So one application for the heat of formation is we can use heat of formation values to calculate the enthalpy values for combustion reactions of hydrocarbons. Okay, more detail on that, a lot of big words. So remember that all hydrocarbons, carbohydrates and other organic molecules, so fancy words for anything that just involves carbon, hydrogen and oxygen in compounds, any of these combust or react with oxygen on high temperature to form water and carbon dioxide. So they've always got the same products, just at different stoichiometric ratios, okay? So if you measure the heat of combustion for a hydrocarbon and you know the heat of formation of water and carbon dioxide, the heat of formation of a hydrocarbon can be easily calculated, okay? Graphically, you've got some carbon, hydrogen, oxygen compound, okay? You're going to react it with oxygen and it forms carbon dioxide and water, some stoichiometric ratio there, okay? If you know the heat of formation on this side, okay, of how many waters and carbon dioxide you have in that reaction, and you'll get given either the heat of formation of that molecule or the heat of combustion or the enthalpy from the combustion reaction, you can work out one or the other, okay? So problems like this will give you the info for the heat of combustion, the heat of formation for water and carbon dioxide, and give you one of these two and ask you to derive the other, okay? So for here, the enthalpy is going to equal the heat of formation of the products, which is some number of moles of carbon dioxide and some number of moles of water, minus the heat of formation of the reactants. Okay, and here are the values here. You won't need to remember them. They're not on your data sheet, but if an exam is going to ask you a question about them, they're going to give you these values. Okay, so determine the heat of combustion of liquid propane C3H8 given the heat of formation of all of them. Okay, so the heat of combustion is just the enthalpy for the combustion reaction. So first up, we're going to need to do a balanced chemical equation. I can't talk. So propane, C3H8, and oxygen, and they're going to combust to form carbon dioxide plus water. We don't know how much. We'll find out when we balance. Okay, so 3 carbons, 8 hydrogens. Let me just clean that up a bit. 8 hydrogens. So now on the right hand side we've got 3 times 2 oxygen, 6 plus another 4 from the water, so that's 10. So I'm going to need 5 O2s to get my 10 oxygen. Okay, so determine the heat of combustion. Alright, so should I change colours? Why not? Green's going to be horrible on blue. Let's do it in black. So my enthalpy for this reaction, or my heat of combustion, because it's a combustion reaction, is going to equal the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. Okay, same formula. Okay, big brackets. My heat of formation for my products, well, I've got 3 moles of CO2, so I've got 3 times the heat of formation of CO2 and 4 times the heat of formation of H2O minus, big bracket, the heat of formation, the sum of the heat of formation for the reactants. Well, I've got 1 times my propane, so the heat of formation of C3H8, plus 5 times the heat of formation of oxygen. Okay, let's start subbing in values and thinking about it. So we've got 3 times the heat of formation of CO2, it's given up here, negative 393 kilojoules per mole. And we've got 4 times the heat of formation, which is negative 285 kilojoules per mole, minus the heat of formation of propane is negative 283, and plus 5 times, hang on, the heat of formation of oxygen is not listed. And it's not listed because the energy to take O2 from its component element in its natural state is O2. So there's no difference in energy. So it's 0 kilojoules per mole because it's an element in its natural state. So I might rewrite that as 5 times 0 kilojoules per mole. And I'll put a 0 there so you don't think it's an O. Alright, let's put it in our calculator. We have 3 times negative 393 plus 4 times, well, it's negative, so I'm going to do minus 4 times 285, and then I'm going to minus my negative 283 plus 283 and a 0, so that equals negative 2036 kilojoules per mole. So the enthalpy for the combustion reaction for propane, or the heat of combustion for propane, is 2036 kilojoules per mole heat given out or liberated sometimes. Alright, calculate the heat of formation of butanol given the heat of combustion and the heat of formations, okay? So notice here, I'm not asking for the heat of combustion, I'm asking for the heat of formation given the heat of combustion, okay? We're still going to approach it the same way. We've got butanol, and I've given you the formula there because you can't derive the formula from the name yet. You will in Year 12. C4H10O, and we're combusting it with some oxygen. And it's giving, because it's carbon, hydrogen, and oxygen, it's giving carbon dioxide and some amount of moles of water. And let's balance. 4 carbons on the left. I'll put a 4 on the right there. 4. And how many hydrogens we've got? We've got 10 on the left. So I need 5 on the right. Okay. Now, how many oxygens have I got on the right-hand side? Notice how I left the oxygen to last because it's by itself on the left. So I've got 8 from the carbon dioxide and 5 from the water, so that's 13, minus the 1 that's on there, so it's 12, so I need 12 from O2, so I need 6 O2s. Okay, so the heat of combustion, or the enthalpy for this reaction, is going to equal the sum of the heat of formation for the products, get it around the right way, where they're ending, minus the sum of the heat of formation for the reactants. Okay? Help if I could spell. And I didn't do H. Oh, dear. Let's keep going. Okay. So this, if I expand it out but don't put numbers in yet, is going to equal big bracket the heat of formation for the product. So we have 4 times the heat of formation for CO2 plus 5 times the heat of formation for water minus, for the reactant side, 1 times the heat of formation for C4H10O and 6 times the heat of formation for oxygen. Okay. The question is asking, we've got this value, we've got that value, we've got that value. It's asking for that value. Now, it hasn't given us that value because the heat of formation of oxygen, it's already as it's found in its natural state, so that cancels out to be 0. Okay? So, what we can do is rearrange it and put the heat of formation on one side. Okay, so it's negative in front of the heat of formation, so I'm going to put it on the other side. So the heat of formation of C4H, oh, not a big 10, H10O is going to equal, well, what's left on the other side? 4 times the heat of formation of CO2 plus 5 times the heat of formation of H2O, and I need to get rid of the heat of combustion from the other side minus the heat of combustion for C4H10O. Okay, so let's substitute in. 4 times the heat of formation of carbon dioxide is 4 times negative 393, plus 5 times the heat of formation of water, which is negative 285 kilojoules per mole, minus the heat of combustion is negative 2677 kilojoules per mole. Put it in my calculator. I'm just checking out if my signs are alright. Products, yeah. Minus that, so if I add that to the other side, I've got to minus that. Yeah, I think it's alright. Let me know if I've got it wrong. 4 times negative 393 minus 5 times 285 minus 2677 equals negative 5,674 kilojoules per mole. It's a large number, but there's a lot of bonds in there, so that will take a lot of energy. So I'm not panicking too much about that large number, but please tell me if I got it wrong. Okay, if you want some more problems, there's a worked example from the textbook and the textbook questions, and I'll see you next video.